All right, so today we're going to be going over chapter 19. This is starting the very last part of the course, what's called inference. Inference deals with taking sample data and applying it to the general population. So what we're going to do today is talk a little bit about sampling, a little bit more than we've done before. And then I'm going to show you some software that we're going to be using over the next couple of weeks. Actually for the rest of the course pretty much, which will help us do this thing called inference. So, I think to get started, we'll go to the PowerPoint. Okay, so this is chapter 19, diversity of samples from the same population. And by the way, our quiz next week will cover chapters 17 and 19. Okay, that's a quiz on Monday. That's quiz number 7. All right, so again, there's these thought questions at the beginning of each of these chapters. So we'll look at this one. So suppose that 40% of a large population disagree with a new law. Parts A and B, think about the role of sample size. So if you randomly select, let's say you randomly select 10 people, do you think it's absolutely sure that you will get exactly 4 people that disagree with the law? Would you be surprised if only 2 in the sample disagreed? How about if none disagreed? So how about anyone wanted to mention this or comment on this? If we had only 10 people in the sample, you think if we would get exactly 40% of the people disagreeing with the law? Or can we have some variation around that?
You can have some variation.
Yes, of course, right? Can you get 2? Yeah, sure, you can get 2. 0 disagree out of 10? Well, that's possible too. Maybe not as likely as 2, but with only 10 people, it can happen. But if you have 1,000 people in your sample, again, the question is, would you get exactly 40% or 400 who disagree with the law? Is that likely? Shout out if you think that's likely that you would get exactly 400 people who disagree with the law.
It's not likely.
Not likely, no. How about it? Would you be surprised if you got only 200? Remember, we have 1,000 people here now instead of 10 in our sample. So
It would be surprising because the sample's larger.
That's right. That's right. It would be harder in this case to see only 200, right? How about none? Of course, out of the 1,000, yes, right? That would be extremely surprising. So the point is that the more people that you have in your sample, this is what we'll learn today, the more people you have in your sample, the closer the results in the sample should be to the actual population value. So if the population's 40% disagree, then a larger sample should be closer to that, no matter what sample you use. At least the probability should be pretty high that it should be pretty close to that 40%. So 200, that's 20%. That sounds pretty unlikely. 0, that sounds very unlikely. All right. Next things here says, explain how the long-run relative frequency interpretation of probability and Gambler's fallacy helped you answer parts A and B. So for part A, which of these 2 concepts apply more, the long-run relative frequency interpretation or the Gambler's fallacy? Which one of those apply to your answer for part A?
Gambler's fallacy.
That's right, because it's a small sample, right? So once again, most people, not all, but most people would think that you should get close to 40%, right? Even with a small sample. But remember that the 40% deals with long-run relative frequencies. So 1,000 people would be more like a long-run relative frequency, right? As opposed to a sample of 10. So the sample of 10 is a small sample, so the Gambler's fallacy could kick in. The sample of 1,000, the relative frequency interpretation, which is, all right, good. Move on to the next one. All right, so suppose at a large university, the mean height or mean weight of women at this university is 135 pounds, and with a standard deviation of 10 pounds. So it says here, recalling the empirical rule for bell-shaped curves, what range would you expect 95% of the women's weights to fall? So we're going to assume here that this is a norm, that weight is normally distributed or bell-shaped. If you anybody remember what the empirical rule would say to determine the range of values for 95% of the women? You may have, some difficulty remembering this. Maybe somebody does remember it. Anybody remember this? How many standard deviations away from the mean would this be?
3?
Not 3.
1.
Not 1.
2, I'm guessing.
Only 1 left. It's 2. It's 2. So 2 standard deviations from the mean. So how do we figure it out? Well, we take the standard deviation value of 10 and multiply it by 2. And then we subtract in this case, 20, because 2 times 10 is 20. We subtract the 20 from 135 to show the lower end of the range, and add 20 to 135 to show the upper end. So it would be 135 minus 20, 115 would fall in the lower part of the range, and 155 would fall in the upper range. And that would be where you would expect 95% of the women's weights to fall, between those 2 numbers. All right, suppose you randomly sample 10 women at the university. How close do you think their average weight would be to 135 pounds? You think it would necessarily be close, or? And the hint is, think of the gambler's fallacy in this case here. Do you think it would be close, or do you think it could be pretty far away?
Pretty far away.
Yeah, it could be, right? It could be far away. But do you think that the range is as wide as it would be for selecting one person? Or do you think the range should be narrower? I
Wide.
haven't learned this yet, but I'm sorry, go ahead. What was that?
Wide.
It should be, you mean wider? It should be wider if you have 10 women?
Oh, if you have 10 women?
Yeah, if you're taking the average of 10 women's weights, do you think the range is, and let's say you have multiple, let's say you sample, let's say everybody in the class here samples 10 women. Do you think that the range of sample means,
It
the
would be
range of average weights would be wider or narrower than if you just looked at one person?
narrower.
Narrower, right, it would be. That's what we're gonna find out. How about 1,000 women? Do you expect that average to be closer to 135 than for 10 women? And the answer to that is yes, because with 1,000 women, all right, when we take the average of 1,000 women, that average weight should be closer because there's more people in the sample. There's more women in the sample. So it should sort of average, the extremes should average themselves out, and we should expect an average to be closer to that 135, which is the mean weight of all women at the university. So that's the general rule. The larger the sample, the better the sample estimate is. All right, the better the sample estimate is. All right. All right, suppose we have a survey of 1,000 individuals randomly selected. There's a margin of error 3%. Now remember, we only touched on this in an earlier chapter. A margin of error means that you take that number and add it and subtract it from the sample value that you're looking at, and then that's your range. All right, that's your range. So it says here, suppose 25% of adults believe in reincarnation. and we have 10 polls are taken, each asking a different random sample of 1,000 adults about the belief in reincarnation, would you expect each poll to find exactly 25% of the respondents expressing belief in reincarnation? I think we already answered this, right? What's the answer? Do we expect exactly that at 25%? No, right? We would not. We would expect some variation from each poll would be different from each other, and most likely they would not, probably none of them would match exactly the 25%. If not, right, into what range would you expect the 10 sample proportions to reasonably fall?
Between 28 and 22?
That's exactly right. Yes, you just take your value of 25% and add and subtract the margin of error. That's exactly right. All right. So if 25% is the assumed population proportion, okay, 25% of the adults in the population believe in reincarnation, then you just add and subtract that margin of error. And so when you subtract 3% from 25%, you get 22%. When you add it, you get 28%. You're exactly right. So there's a very good chance that those 10 sample proportions would fall in that range. All right, so let's just read through this here, and then we'll move on. So when you do this thing called inference, which is what we're going to be doing, which is taking information about a population, taking information from a sample and generalizing it to the entire population. First thing we have to do is come up with a question about the population. We need the question first so that we know what variable to measure. Once we know that, we then collect our sample and ask or measure that variable in that sample. It's either a question or a measurement, something like that. And then with statistics, we're going to determine how close such an answer based on the sample would tend to be from the actual answer for the population. Now remember, when we do sampling, we don't know what the population answer is, right? Otherwise, why bother with the sample if we know the answer? So sampling is done because we don't have the resources, or it's impossible to get the information about the entire population. But as a result of doing sampling, our samples are going to be what? Well, they're going to be different from each other. If multiple people take the same type of sample from the same population, you're going to get different answers to the question. So what we have to determine is how close are those samples to the actual population value. And this seems like an impossible task because we don't know what the population value is. So we need a little bit of trickery, I guess we call it trickery, to figure this out, all right? So suppose through this trickery, through the mathematics that we use, suppose most samples are likely to provide an answer that's within 10% of the population answer. That's the margin of error, all right? Suppose that's true. If that's true, then we can also say that the population value is expected to be within 10% of your sample value. Doesn't that make sense? So if the samples, if samples are supposed to be, or likely to be within 10% of the population value, that also must mean that the sample value must be within 10% of the population value. All right, and that's what that's the trickery I'm talking about. Even though we don't know anything about the population, we can use the sample and say, all right, I think based on the math that I'm using, I'm going to be within 10% of the population value. All right, so you come up with the sample is you consider to be a decent guess about the population value. All right, we'll see how that works. Here's an example here. Looks kind of weird, but suppose we have a population, people, and suppose some of the people have a gene, and the X means they have the gene, and suppose some people don't. Obviously, the others don't. So we have a happy face. So I guess this gene is not a good thing. That's why we put a happy face here. So if you don't have a gene, you have a happy face here. And if you do have the gene, you have an X in a little box. But here is a slice of the population, and some people have X's, which means they have the gene. Some people have smiley faces, that means they don't have the gene. So you can picture population like this. Okay. Suppose you take random samples out of that population. And the sample size, if you count the number of smiley faces and X's for each of these samples, there's 25 of them. All right, so you just count across, there's 25. Each of the samples have 25. So we want to know the proportion of each sample that have the gene. So if there's 25 altogether, we just do what? We count the number of X's, right? The boxes with X's. So sample number 1 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 out of the 25 here are X's, X boxes. 13 out of the 25 have smiley faces. So the proportion with genes is 12 divided by 25, or 48%. All right, so that's how we calculate it. It's pretty easy, right? I hope you agree with that. So the second sample, you count the number of people with genes, with the X's, and we have only 9 in the second sample, so that's 36%. The third sample, numbers that have these X's here, have the genes, is 10, so that's 40%. And then the last one, there's not too many of them. There's only 7 boxes here. So 7 out of the 25 have the gene, 28%. So these are the sample proportions. Sample proportions of the number of people who have genes. Sample of what? Size 25. 25 people in each sample. How many people in the population? Could be millions of people, right, in the population. But we're just taking a sample of size 25 out of that population. Notice that each sample has a different answer. The question is, and let's face it, when you do sampling, you don't know which of these samples you're going to get, and there may be millions more of these types of samples, right? There could be millions of these, maybe zillions of them. Who knows how many? You could picture each one of those samples have a different answer. Maybe some of them have the same answer, but many of them have a different proportion, sample proportion. So you as a researcher, you do a random sample and you determine the person has this gene or not through some sort of genetic test or something, and you record your sample proportion. But that's the one sample that you're going to have to work with, and you're not going to work with any other sample. So the question is, how close is that sample proportion to the actual population proportion? That's really what we're talking about here. Most likely, it's not going to be equal to the population proportion, and it's, likely that it's going to be different from other samples that you could have picked. So here is the rule for sample proportions or how to do statistics with sample proportions. So let me go through them, and then I'll sort of explain what this all means. Number one, it says there exists an actual population with a fixed proportion who have that trait. Well, yeah, right? I mean, if it's a genetic trait, it would be a fixed number of people who have that gene. Or maybe for some other type of research, maybe there's not a fixed proportion in the population, but there exists some sort of repeatable situation for which a certain outcome is likely to occur with a fixed probability. Right? Maybe something is happening over time. We don't know the actual proportion over time, but we could guess at it. We can come up with an estimate of that. All right, so that's what they mean by that. Number two, a random sample is selected from the population. All right, of the person who's observed to have that trait, like having that gene. Or you, again, in this time, you do a random sample and repeat the process of selecting people. And you just make sure that each of the people that are selected are independent, that those observations are independent of one another. And number three, the size of the sample, number of repetitions, okay? We want to make sure it's large enough. It's large enough. It's large enough for what? To see here, it says at least 5 of each of the 2 possible responses. Now, by the way, if you look on the corresponding page in chapter 19, it actually says it says 10 instead of 5. I see some textbooks that say 5, some textbooks that say 10. The question is, what would we use in a test if we ever needed to ask about this? I would say use what's in the book, which says 10. All right, we could say the book is the authority on this. So the slides say 5. That could easily be replaced with 10. All right. So the book is the final authority. We'll say 10. All right. So here's an example. All right. A pollster wants to estimate proportion of voters who favor certain candidates. Voters of the now, what they're saying, what they're showing you here is what is being measured and who are those who are being measured. So the voters are the population units. They're the ones who are being asked, who is your favorite candidate, all right? And the opinion of interest, or the question that's being asked, is who do you favor? Which candidate do you favor, all right? So those are the types of questions that we're talking about here. And then, of course, we would then count the number of people who favor candidate A versus candidate B. All right, here's another example. TV rating firm wants to estimate the proportion of households with television sets tuned to a certain TV program. All right, Nielsen is an example of a firm that does this. Collection of all households with television sets, that's the population. And what is the trait of it? They call it a trait, but what's being measured here? It's whether they're tuning into this television program or they're not. They're either not watching this program, watching something else, or just doing something else. All right, and here's some more examples here. A manufacturer of soft drinks wants to know what proportion of consumers prefer new mixture of ingredients compared to an old recipe. Who are what's the population? All consumers. And what is being measured is their preference for the new formula over the old formula. So I hope you get the idea of what they're talking about here. They're just saying who is being measured and what is being measured, okay? Now, here is the little bit of math that you do need to know, just a little bit of math, not much. This is called the rule for sample proportions. Let me explain what this means. Now remember, when you do sampling, you're going to choose one sample of a certain size. All right. When I say size, I'm saying how many people are going to be in the sample. So if there's 25 people in your sample, that means your sample size is 25. All right. Now you chose one sample. There could have been many samples that could have been chosen by you or by anyone else. And there could be, you could list them. Maybe you would need a computer to list all of them because there could be millions or zillions of these samples of size 25, for example. But you could picture listing all of them. And for each sample, you could measure the proportion of those people who, for example, liked candidate A versus candidate B. All right. So we're just counting the number of people who like candidate A, maybe, and finding the proportion of everyone in the sample who like candidate A, just like we did earlier when we did this calculation. All right, we just took the number of people with that particular trait, in this case, the person with the gene, and we counted them and divided by the number of people in the sample. The same thing here. Now, can you picture, I hope you can picture that you could have numerous samples with a sample proportion. Each one has its own sample proportion. If we could make a list of all those sample proportions for each possible sample, and then take the average or mean of all those numbers, okay? What we would find, which is really interesting, is when we take the mean of all those sample proportions, it mathematically should be equal to the true proportion for the entire population, okay? So we list all of the sample proportions, including the one that you have, the one that you actually chose, your sample, but we list all of them. And then we graph them on a graph. And what we would find is that the graph would look bell-shaped, with the mean being equal to the average of all those sample proportions for all those samples that we could possibly list. And here's the standard deviation for that curve. It's the square root of the population proportion, and you have to write it down as a decimal, times 1 minus that population proportion divided by the size of your sample. It's a square root of that ratio. Okay? And that's called, that's the standard deviation. That's the spread of this bell-shaped curve. Okay? This curve is the curve of all possible sample proportions. So let's do an example of this. Suppose 40% of all voters in the US favor candidate X. Here is the pollsters take a sample of 2,400 people. What sample proportion would be expected to favor candidate X? Now, this question it sounds like it's asking for one number, right? What sample proportion would be expected? But what they're actually asking for is a range of values, because we really wouldn't know what that, if we did a particular sample, we wouldn't know what the sample proportion would be ahead of time. But we could say with, let's say, 95% confidence, almost 100% confidence, with 95% confidence, we could say that we would expect that sample proportion to be between two values. How would you figure it out? Well, we could calculate this, this square root, the standard deviation. So in this case, 40% is your population, at least your estimated population proportion who favor candidate X. So we would say the square root of 0.4, which is 40%, times 1 minus 0.4 divided by the sample size is 2,400. If we took the square root of that ratio, we would end up with 0.01. Now, if we assume this is a bell-shaped curve, a normal curve, then the empirical rule says that there's a 68% chance that the sample proportion is going to be between 39% and 41%. Now, how did we come up with that? Well, 0.01 is 1% when we multiply that by 100. So 68% is going to be, it's going to be the mean of 40% plus or minus 1 standard deviation, which is 1%. So 40% minus 1 is 39, 40% plus 1% is 41. And that's why they're saying 68% chance that the sample proportion that you're going to choose is between 39% and 41%. All right. There's a 95% chance that the sample proportion that you choose is between 38 and 42. Why? Because 95% is plus or minus 2 standard deviations from the mean. If a standard deviation is 1%, 2 standard deviations is 2%. And if you add and subtract 2% from 40, you get 38 and 42. That's the range of values. And then the last one says almost certain. That means 99.7%. This is what the empirical rule says, is plus or minus 3 standard deviations. Again, 1% times 3 is 3%. And we subtract 3%, we get 37. We add 3%, we get 43. So it's almost certain, 99.7% certain, that the sample proportion will be between these two values here. So that's the answer to the question. What sample proportion would be expected? Well, it depends on what probability do you want? What chance do you want? Do you want a 68% chance of being right? Or do you want a 95% chance of being right? Or do you want to be almost certainly right? And these are the ranges that you would select based on these probabilities. That's what the empirical rule is stating. All right. Any questions about what I've covered here? Because it's not a easy thing to understand, but it is, I hope, understandable for you. All right. Now, let's look at this slide here, see what it says here. You want to estimate, in this case, the average weight loss for somebody who attends a national weight loss clinic for 10 weeks. Well, let's say somebody knows this. You don't know it, but somebody knows that the population of people who go through this weight loss clinic, they average a loss of 8 pounds and have a standard deviation of a loss of 5 pounds. If weight losses are approximately bell-shaped, it says here 95% of the individual weight losses will fall between -2 and 18 pounds. Now, what's -2 pounds lost? That means that actually a gain of 2 pounds. I guess people who gain weight from a weight loss program wouldn't be too happy about that. But that's possible, right? Somebody could gain 2 pounds. And it could be all the way up to 18 pounds lost. So we're saying we're 95% of the, if we selected somebody at random, 95% of the weight losses will fall between those two values. Now, how did they come up with that? Well, 2 standard deviations from the mean is 95%. That's the empirical rule. So we take our standard deviation and multiply it by 2, because we want 2 standard deviations, and we add and subtract 10 from 8. So 8 minus 10 is -2. 8 plus 10 is 18. So that's how they came up with those 2 numbers. Suppose we have samples. We end up with samples, okay? And how many are in each sample here? Let's see, 2, 4, 6, I think 25, right? Maybe. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 20, yep, 25. So there's 25 people that are selected in each sample. And here are our sample means for each of these samples. Now, remember, the population is 8 pounds, right? And the standard deviation is 5 pounds. So notice that the mean of the first sample is 8.32 pounds. If we just add up all of these numbers and divide by 25, do the same for the second sample, third one, and the fourth one, and they have their, of course, individual standard deviations. So each sample gives a different sample mean. They're relatively close to 8. Sample standard deviations relatively close to 5. All right. So the samples are, decent estimates of the population value. So here we're not dealing with proportions anymore. We're dealing with something that we're measuring, such as what? Weight loss, right? For a weight loss program. So we have also a rule for sample means. And this one actually, if you were taking a regular statistics course, we would talk about something called the central limit theorem and go into that. But here we're going to just basically generalize it and put it into English for you. There's 2 possibilities when we're measuring sample means, and we have a bunch of samples. Number 1, the population of measurements, if the population of measurements is normal or bell-shaped, then a random sample of any size is measured, and we will assume that that is also bell-shaped, all right? Or number 2, in a more likely case, we don't know anything about the population, or it's not bell-shaped, all right? The measurements aren't bell-shaped, but we have a large enough random sample that we can assume that the frequency curve of the sample means for every possible sample is bell-shaped. And what's the sample size that we normally need as a minimum size? Typically 30. But sometimes the book says sometimes we need a larger sample size. But for this course, we'll assume 30 as a minimum sample size. So if our population is not normal in shape, to get a normal shape, normal bell-shaped curve for the list of all means for every possible sample, then we need a sample of at least size 30. So let's just do an example so this is clear how this works. So getting back to the weight loss clinic. So weight loss clinic is interested in average weight loss for participants in this program. We're assuming a bell-shaped curve. So when we do our sampling, we can have any number of people in the sample. We don't need 30. We could have 20 or 25 if we want. And that's because the population is the population for this measurement of weight loss is bell-shaped. Here's another example here. Suppose you're interested in the average age in which left-handed adults die, assuming they live to at least 50 years old. Now, it says here the ages of death are not bell-shaped. All right, so assume it's not bell-shaped. So we need, in our sampling, when we do sampling, we need at least 30 people in our sample. All right, so I hope that's clear. If we don't have 30 people, we have less than 30 people in our sample, and we have to make sure that our population is bell-shaped. The values that we're measuring are bell-shaped. And if we're not sure about it, or we know that it's not bell-shaped, we have to have at least 30 people in our sample. And here is the what we use for the standard deviation. All right. So first of all, once again, if you're measuring something like weight loss, it's not a proportion, but we're measuring weight loss. We're going to probably be measuring the mean weight loss for everyone in our sample. We want the frequency curves of means from various samples to be approximately bell-shaped. So what does that mean? That means if we could possibly list all possible samples, right? If we could list them all that we could have selected, one of which we did select, but we could list all the possible means, all the possible samples, and then took the mean of maybe all the weight losses for each person in the sample, for each sample, we would have basically a list of means, of list of averages. And if we could graph that, and it's bell-shaped, then we would find two things. Number one, that the mean of this curve would be the same, equal to the mean of the actual population. And number two, that the standard deviation for this curve would be the population standard deviation divided by the square root of the sample size. So here's just an example of this. So suppose again that the mean weight loss in the population is 8 pounds with a standard deviation of 5 pounds. And suppose we take a random sample of 25 people, all right? Now we're assuming here, by the way, we're assuming that weight loss is bell-shaped, all right? Because our sample size here is less than 30, we have to make sure that the population itself is bell-shaped. So we'll assume that, all right? What is the standard deviation that we're going to use for this bell-shaped curve? Well, the population standard deviation is 5, but there's 25 people in our sample. So 5 divided by the square root of 25 is equal to 1. So we would say the following. Now this is maybe a little confusing to you, but let's go through it. Using the empirical rule, since this number here is 1, we would say 8 minus 1 is 7. 8 plus 1 is 9. We would say 68% chance that the sample mean is going to be between 7 and 9. Now, when I say sample mean, what am I referring to? I'm referring to if we select a sample of size 25 at random from a list of all possible samples of size 25, we would expect that the sample mean of those 25 people would be between 7 and 9 pounds. We multiply this 1 by 2, we get 2. We get 8 plus or minus 2 pounds, or 8 plus or minus 2 standard deviations. 95% of those of the sample means is between 6 and 10 pounds. So 95% chance that the sample that we choose will have a sample mean between 6 and 10 pounds. 6 is 8 minus 2, and 10 is 8 plus 2. And then you're almost certain, or 99.7% certain, that the sample means between 5 and 11. That's because 99.7% is plus or minus 3 standard deviations. 1 times 3 is 3. 8 minus 3 is 5. 8 plus 3 is 11. Now, this might be confusing to you. Why did we select 1 as our standard deviation and not 5? Right? Because that's what we did before, right? In our examples before. We go back. Let's just go back for a minute. I think we have an example. Here we go. All right. No, that's not it. I think we have an example somewhere here. We don't. So I'm bad. I thought I had an example here. Well, let me just say this again. Suppose we selected one person from a population, and we want to use the empirical rule. We want to know what's the chance that that person would have, what would be their chance for their weight loss? And we would say, all right, if the average weight loss is 5, or excuse me, the standard deviation is 5 and the average weight loss is 8, we would say, all right, there's a 68% chance that we would have between 8 minus 5 or 3, or 8 plus 5 is 13, right? That's the way we would do it. If we were just looking at one person, we would simply say there's a 68% chance that one person would have a weight loss of 3 pounds or up to 13 pounds, between 3 and 13 pounds. But that's not what we're asking here. What we're asking here is, we're not selecting one person, we're selecting a sample of 25 people. And we're measuring the weight loss for all 25 people, and then we're taking the average of those 25 weight losses, the mean. And we're asking the following question: what's the chance that that sample will have a mean? All right, what's that mean going to be for that sample 25? So we're now dealing with the mean of 25 people. And so this is what we're going to use as our standard deviation. We're going to take our population standard deviation and divide it by the square root of the number of people in our sample. And this is the number we're going to use as our standard deviation. And we're going to add and subtract that to get our result. 68% between 7 and 9 pounds, and 95% between 6 and 10 pounds. So I hope you understand the difference of what I'm saying. Here we're dealing with the sample mean of 25 people, as opposed to looking just at one person. What happens if we increase the sample size? Suppose we have 100 people in our sample instead of 25 people. Then this formula that we're using, for our standard deviation, it's our population standard deviation divided by the square root of the sample size. Now we have 100 people in our sample. Notice now that the standard deviation that we use is 0.5 pounds. So when we want to know what's the estimated sample mean going to be, you're going to say, well, according to the empirical rule, there's a 68% chance that our sample mean is going to be between 7.5 and 8.5 pounds. Why 7.5 and 8.5? Because 8 minus a half is 7.5. 8 plus a half is 8.5. All right. So what happens is, as we increase the sample size, our ranges here become more narrow. They become better estimates. All right. They get closer to what? They get closer to the actual population value of 8 pounds. So I hope you see where we're going with this. The larger samples tend to result in more accurate estimates of population values than do smaller samples. And you can see it through this formula. The larger n is in the denominator, the smaller this number is, and the more narrow these ranges are. When they're more narrow, then we know that the sample that we have is close, pretty close to the actual population value. And this is the key to understanding why we can use a small sample to estimate a population value, like a mean. Okay? Any questions about that? I hope you're all awake. I don't see anybody's face here, so maybe you're all doing something else. I hope not. All right, so let me see what time it is. I guess we still have 25 minutes left. I do want to finish this section, this chapter here, and then I want to go into the software that you're going to need to know about and use for the rest of the course. So anyway, there are two types of situations that we're going to look at. That is proportions and means, averages, all right? A proportion of a population in one category versus other categories, or the mean of a measurement variable, like weight loss. Those are the two types of things that we will be estimating from the sample to the population, and that's it. There's nothing else in this course. Now, I have to clarify a little bit. Sometimes when we will be looking at some of these things, we might be looking at a proportion and comparing it from one group to another. So we might be actually comparing two groups, men and women, two age groups, whatever, looking at proportions or looking at means. So we sometimes will be looking at two possible populations also. But don't worry about that, we'll be getting to that. And there's two types of statistical techniques that we're going to be examining. One of them is called a confidence interval. A confidence interval is an interval of values that estimate the true value of the population. We've been starting to do that already. The other thing is called a hypothesis test. And a hypothesis test is basically, we will be looking at two hypotheses. One hypothesis about maybe a population mean would be something like, I think the population mean is 30 for whatever we're measuring. And then you as a researcher think, well, I don't think that's true. I think it's 20, I think it's 40 or something else. You'll do some research, you'll take a sample, you'll do some measurements, and then you'll say, all right, I have enough evidence to reject the common idea that it's 40, and I think it's less or more. So that's what's called hypothesis testing, and we're going to be learning more about that a little bit later. All right, so let me just see how much is left here. Just 2 slides, so let's look at the 2 slides. This is a case study. Do Americans really vote when they say they do? So a telephone poll of 800 adults, 50% reported that they had actually voted, all right? Now, a committee for the study of American electorates states that only 39% of Americans vote. But in this particular poll, it says 56% said they voted. The question is this committee's idea of 39%, is that really right? Well, we'll assume for now that it's the population proportion, 39% vote. The question is this 50% chance, 56% that comes out of this poll, does that sort of like say, well, this 39% is not quite right? Well, that's the sort of thing that we'll be doing starting next week. We'll be looking at that sort of question. So basically it's saying here, could the results of the poll simply reflect that by chance, all right, that we just selected this sample by chance out of a population which has an actual proportion of 39% people voting. Is 50%, is it possible to have a sample 56%, or is it so unlikely that we doubt that the 39% is true? So how do we do it? Well, remember, this is the standard deviation of our list of all possible sample proportions. Right? So we take our 39%, which is the population estimate, we plug it into here, and we do 1 minus 0.39, and we divide by the sample size of 800. And this is what? This is our standard deviation, 0.017. Now we need to convert that to a percentage because we're looking at percentages here. So this is 1.7%. So what can we say? Well, this is one standard deviation, 1.7%. We want to be almost absolutely certain. We could say something like this. We will be 99.7% certain that 3 standard deviations from 0.39, plus or minus 3 standard deviations 0.39, would be the range of values for our possible samples of size 800. All right, so we'll multiply 1.7 times 3, that's 5.1%. When we subtract 5.1% from 39%, we get 33.9. 5.1% plus 39% is 44.1. So we're saying that if it's true that the population proportion is 39%, then we would expect almost all samples, 99.7% of them, to have proportions that vote between 33.9 and 44.1%. But look at what we came out with our poll, 56%. That's really unlikely, isn't it? That's so much bigger than the 44.1% here. Remember, 99.7, we expect 99.7% of the samples to be between these two values. So the point of the matter is that this 56% result that we got from our sample casts doubt on the 39% that's being reported by this organization. If this 39% was correct, this 56% would be so unlikely, the probability of it happening would be practically 0. Notice if we calculated the standard score, the z-score for this 56%, again, we would subtract the mean, which is 0.39 from 0.56, and divide it by the standard deviation, this standard deviation, 0.017, we get a standard score of 10. This 56% is 10 standard deviations from this mean. So it's virtually impossible to get a standard score of 10 or more. 0, practically 0. So this is the type of thing that we'll be doing later, the type of interpretation that we'll be doing later. This is the type of thing that we'll be looking at when we do hypothesis testing. We'll do a calculation like this, and we'll say, well, my sample is saying very little chance that the hypothesis of 39% is true. Therefore, we have to reject it and assume that it's bigger. Okay, that's sort of what we're showing here. And then for those of you who are interested in formulas, here are some formulas again. I think most of you probably are going to ignore that. So for the next 15 minutes, I want to show you what we're actually going to use in this course to do and remember, let's go back. One of the things that we're going to be doing in the next few weeks for the rest of the course are what are called confidence intervals and hypothesis tests. Typically, if this was a regular statistics course, we would be showing you further formulas and steps of doing these. But instead, what we're going to do is we're going to use what's called simulation, computer simulation, to come up with these confidence intervals and hypothesis tests. So in a sense, we're going to be skipping these more complicated formulas that you would learn in a regular statistics course. And instead, you're going to be learning how to use this software. So I'm going to actually go out of this, go out of that and go to our software program. Let's see if I can find it here. It's called stat key. All right. Now, if you Google it, you would just type in stat key and look for, and actually, let's actually do that now. I'm just, instead of doing this, I'm going to actually just type in stat key. All right. Just one word, stat key. Hit enter. All right. And on my browser, I get stat key lock 5 homepage. Now, what's lock 5 mean? There's a family of statisticians. They're the Lock family, believe it or not. They're like 3 generations of people in this family who are all statisticians, and they all teach statistics, and they created this software program and actually have their own textbook. So you just go right here. It says lock 5 homepage, and that takes you to this screen here. So again, I will be giving you instructions, but you should write this down now. Just write down this stat key that you need to get to. This is the website. All right. Now, I will be showing you in this website how to use all of these things here. The 2 columns that you'll be using starting next week, when we do confidence intervals, it'll be this column right here. It says Bootstrap confidence intervals. Very, very easy to use this thing here. You don't need formulas, but you do need to know how to interpret what you're looking at once you create your so-called confidence intervals. So I'll show you how to use it next week. Notice that it has here, now CI means confidence intervals. Notice it has single proportion and it has single mean here. Now we're not going to do medians and standard deviations. We're just looking at means. We also have what's called difference of means and difference in proportions. And this will be when we have 2 populations. We're going to be comparing populations. So one population has a mean and another population has another mean, and we're going to subtract them and then also look at that. All right, we'll do the same thing with proportions. And then this last column here is for a hypothesis test. We'll use this thing called randomization, and we'll have tests for single mean, single proportion, difference in means, difference in proportions. This thing it says here, test for slope and correlation. In both of these cases, we're not going to be doing that. All right, now in your textbook, let's see if I still have access to the textbook. Let's actually, hold on a minute. There we go. Stop sharing this for a second. And let's see if I have access to the textbook. All right, where are you? That's not it. All right, hold on a minute. Let me just go back here and just give me a second here. I'll get to it. Looks like I lost it, unfortunately. So let me just give me a second here. Looks like I got logged off. I'm going to show you at the end of the chapter. There's something there about simulation. I want to bring that to your attention. Then I'll show you how it's done in StatKey. So I'm going to show you a little bit about StatKey. And then show you some videos that you could look at that tell you a little bit more about StatKey. Just give me a second, I'm almost there. Okay. Here we go. All right, so let me get back to sharing the screen with you. Here we go. This is it. All right, so at the end of the chapter, this is not in the slides, but at the end of the chapter, they talk about simulating proportions and means. And they're using a software program called Minitab to do this. And anyway, here's an example of a simulation. Suppose you have a political poll and you want 2,400 people, sample size of 2,400, right? And you are looking at, and assuming that the population proportion, let's say 40% of people are interested in voting for a particular candidate. And what you're doing here is you're simulating samples of size 2,400 from this population and coming up with different sample proportions. And this is what I mean by a frequency curve that looks bell-shaped. So here are examples of or frequencies. The histogram, the heights of the histogram tells you how many of these samples have a certain proportion. So this is basically a list of sample proportions. How many of them? We did 1,000 of them. So these are 1,000 individual polls. So these are 1,000 samples of size 2,400 each. All right. The population proportion is 0.40. And notice that if you take the mean of these 1,000 sample proportions, you end up with 0.33998 as your mean. And that's really very close to 0.40. So 0.4, the mean of all these samples is very close to 0.40. So basically it's equal to the population proportion. The standard deviation is about 0.01, okay, about 0.01. So when we did that calculation with the square root, it should be very close to this number here, 0.01. All right. So anyway, this is what we mean by a normal bell-shaped curve. Somebody drew this curve around us, and it looks bell-shaped, this histogram. Suppose we did something like this in StatCube. So that's what I'm going to do now. I'll stop sharing this, and we'll go into StatKey. So where are we? Where's StatKey? There we go. Share the screen and so you can see StatKey again. Okay. So here are, this is not something, I'm only using this for demonstrations, but suppose I want to create a sampling distribution through this process of simulation. I'm going to click proportion here. And I want to create a bell-shaped looking curve just like that. So my sample size, I think it was 2,400. So I'm going to type in 2,400 here. I think that's what it was, I believe, right? In the example we're just looking at. Okay. I think it's 2,400 for each sample, and we did 1,000 samples. I'm going to click to tail here, and I'll show you how to use this later date. Right, and then I think the sample proportion was 0.4. So it's not giving me that information. See if I can edit proportion. Here we go. So I'm going to put 0.4 in here for the proportion, population proportion. Now I'm going to simulate it using 1,000 samples. Okay. So this is not going to look exactly what's in the book because this is a simulation. You're going to get different results each time. But this does look bell-shaped, doesn't it? This looks bell-shaped. Okay. Bell-shaped curve. And we would say that 95% of the values are between 0.379 and 0.419. That's what this is saying here. So the mean is 0.40, and it says the standard error, the standard deviation is 0.01 standard error. But anyway, this is what we would expect to find, 95% in between those two values. All right, so this is a simulation, just like what's in the book. You can create lots of samples of a certain size. There's our sample size. There's 1,000 samples of size 2400, and it would create something that looks like a bell-shaped curve.
What are the numbers that are like in the little blue bubbles?
What's up here?
Yeah, are those the standard deviations or?
Those are actually percentage of the points that are in between values. So in other words, it says 0.95. That's 90. See all these black dots here? The black dots represent 95% of all the dots that are listed here. And the 0.025, that's 2.5% of the dots. So in other words, there's 1,000 of these dots altogether. That's what the number of dots are here. The 0.95 says that 950 of these 1,000 samples are black dots here. And there are there's 250 red dots to the right and 250 red dots to the left. We'll learn what this means later, but it's basically saying that 95% of these samples are between, have proportions between 0.379 and between 0.419. And it's represented by these black dots. Every dot here is a particular proportion for one of those 1,000 samples. So, and what's nice about this, if you point to one of them, it tells you, let's see, hold on a minute. If I point to one of these samples, okay, click on it. You see on the right there, they have a sample here. It actually tells you the information about that sample. So I just put my cursor over this one. It says it's the count is 989 out of 24 for that particular sample. 989 out of 2,400, or 41.2% of the people like candidate A. If I put my cursor over to one of these red dots over on the left here, 910 out of 2,400, or 37.9% of that sample like candidate A. See how that works? So it's giving you the information about that particular sample that this computer generated. So each one of these dots represents one of these 1,000 samples, and it represents the proportion of that sample that like candidate A. Okay? Did that answer your question? I hope.
Yeah, I was just wondering what they are. That makes sense though. This is like a lot better than like in high school when I used to have to do this by hand.
Exactly, exactly. So we're going to be using this instead of doing it by hand, doing these calculations by hand. And what was covered in chapter 19 is usually the preparation for what's usually covered in a regular statistics course. If you look in future chapters, chapters 20 and 21, they go through these formulas that you normally use. But in this class, we're going to use StatKey instead. So this, what I just showed you, is a sampling distribution. This is what the chapter was all about. It's we're using a computer instead of actually taking 1,000 samples, which obviously would be, too expensive to do, right? Nobody's going to do that. So we use a computer to generate these samples. We have to assume what the population proportion is, by the way, to generate this. It uses a certain computer, what's called an algorithm, a formula to figure out how to generate these samples. But yeah, it's kind of fun to do this, right? And we can actually increase the number of samples in here. We have 1,000 here. We can click this again and make it 2,000. What if we want 2,240 samples? Well, I click this again and again and then just click this 4 times. Now I have a simulation with 2,240 samples. Each have a sample of size 2,400. And so there are 2,240 of these dots now. Okay. And it changed, the blue changed in here. Again, we'll talk more about this here. But it's saying here that 93.8% of these 2,240 samples have black dots. That means are in between these two values here. And then there's 3.1% that have the red dots on the right and 3.1% that have red dots on the left. Again, each one of these dots represents a particular sample of size 2,400. So you have to kind of get used to what you're looking at, right? And that's why I'm showing you guys this today, just as an introduction. Now, I'm going to go back just for a second to the main screen. And I want to point out to you something that I would recommend for you to look at. If you click the statistics unlocking the power of data here, they do have the they are marketing their textbook. You do have to buy it if you want it. Of course, we're not going to buy it. Here are the Locke family, right? Granddad and dad and whatever. It's Locke family. But along the side here, there are some videos. All right, so if I click videos, I mean, they do have PDFs also, which you can read if you prefer to read about them. If you look at the PDFs, all right. Well, these are written as papers. I don't know if you want to read that. You could if you want to, but I would recommend the videos. And right on the top here are 3 introductory videos. So before the next class, number one, I recommend just going on to this website and just play with it. Play around with it. You're not going to hurt anything. And just see if you just become familiar with what's where, and you can take a few minutes just to play around. But I would watch the introduction to StatKey video. All right, one of the Locke family members, the Robin Locke, she does that video. It takes about 21 minutes. It just tells you how to navigate the whole software program. All right, so just look at that. And then on Monday, when I start doing confidence intervals, if you want to also watch this, you can watch it afterwards if you want, or before. That's our next topic. We're going to simulate these so-called confidence intervals. You could watch that video also. And then, later when we do our hypothesis tests, you can watch this final video on how to do hypothesis tests with StatKey. All right. So very nice program, and it's free. And just play with it. But again, I would recommend watching at least the introduction to StatKey before our next class. That way you're familiar with what I'm doing. All right, any questions, any comments? Are we good? All right, so let me stop sharing. So next Monday, we're going to start looking at confidence intervals with StatKey and show you how that works. Obviously, I will have some written instructions also, some things written up, some basic step-by-step instructions so that you can actually use it. So the quiz on Monday will cover chapters 17 and 19. It will not cover StatKey, by the way, but we will have a quiz that could cover some of the things in StatKey later, but not for Monday. So Monday, just chapter 17 and 19. So we will continue on Monday, and then we'll have our quiz just like we've had. That will be quiz number 7. Any questions? Any comments?
Are there any calculations we have to do for Monday's quiz?
It's possible, yeah. Simple calculations like calculating the standard deviation for these frequency curves, those formulas, like for the portion, the square root formula, and for the other one, for the mean, the standard deviation divided by the square root of sample size. Yeah, you should know how to do that. But very simple things. I'm not going to ask you anything complicated. All right. So something very simple. But again, it's open book, right? So have a calculator by your side just in case you need to do something like that. I haven't created the quiz yet, but I anticipate there might be a couple simple calculations in there. Anything else? All right, so I'm going to turn off the recording.